Hello, math humans. We're going to do 2.6b today. We're going to be doing more work with related rates. And our objectives are, math. So first example, and I've pre-written the examples today just so we have a little bit less time to watch me write. A conical tank, vertex down, is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So just like with the problems yesterday, the first thing that I should do is draw a picture. So here's my cone, tipped down. It's going to be 10 feet across, so that means that the radius is 5 feet. And it tells me that my cone is 12 feet high. Okay. It says that the water is flowing into the tank at a rate of 10 cubic feet per minute, so my dV over dt is going to equal 10 cubic feet per minute. I'm looking for, find the rate of change of the depth, so I'm looking for dH dt when h is equal to 8 feet. So how fast is the water changing at that point? And my volume equation is 1/3 pi r squared h. Now, if you'll notice with this problem, unlike the ones that we did yesterday, now I have 3 variables instead of 2, but I'm only been given 2 rates, or I'm trying to find a rate. So that means that I would have a dV dt, a dr dt, and a dH dt. That's just too many variables, and they didn't give me that. So I'm going to develop a way to get rid of my extra variable. And so this is a classic situation in these problems. So I'm going to set up a ratio r is to h as 5 is to 12. Okay? R is the problem variable because I don't have a dr dt, so I'm going to solve for r, and I'm going to get 5h over 12. And now I'm going to take this r and I'm going to substitute it into this equation. So then I'm going to write it down here. My volume is equal to, let me scoot up a little bit, pi over 3, it's just a constant, r squared, 5h over 12, quantity squared times h. And I'm going to rewrite this again. So here's the pi over 3. I have 25h cubed over 144, and I'm just going to leave it like that. Okay? So now I'm going to take the derivative, so dV over dt is going to equal pi 25 over 3 times 144 is going to stay, times 3h squared, that's the derivative of h cubed, dH over dt, the 3's cancel, and so it's going to equal 25 pi h squared over 144 dH over dt. Remember, the goal in this particular problem is to solve for dH dt. I know that my dV dt is going to equal 10, so I'm going to write that down there. So when I solve for dH dt, dH over dt is going to equal 10 times 144, and I'm going to divide by 25 pi. Remember that my h is going to be 8, so times 8 squared. And when I do this math, I get 9 over 10 pi. Let's talk about the units. I have a height, which is linear, feet. Time in this problem is minutes. So now I can write my conclusion statement in dH over dt is 9 over 10 pi. It's also okay if you just have a decimal for this. Either is okay. Feet per minute when h is equal to 8 feet. Because remember that the rate of change is different at every point along the curve or along whatever is happening. Okay? All right, now let's do our second example. So for this one, we have a TV camera at ground level, which is 2,000 feet from a rocket, is filming the liftoff of the rocket that is rising vertically according to the position function S of t is equal to 50t squared. It tells us that S of t is in feet and t is in seconds. Find the rate of change, derivative, in the angle of elevation of the camera tracking the path of the rocket 10 seconds after liftoff. So get ready for my spectacular artwork. So here's my rocket. The position of the rocket is going to be 50t squared. That was given. We know that I am 2,000 feet away. Here's my little camera. And then this is going to be theta. And we assume that a rocket goes straight up. Okay? So I've written down my position function. And I'm looking for d theta dt when time is equal to 10 seconds. Okay? I need a value over here, so I'm going to write that S of t is equal to 50t squared. And then I'm going to do S of 10 is going to equal 50 times 100, and that's going to be 5,000 feet. So that's going to be the position of the rocket after 10 seconds. Alrighty. So the equation that I'm going to use is that the tangent of theta, because I'm looking for theta, is going to equal S of t over the 2,000. And that's just straight trig. That's just y over x. Okay? So what I want to do is take the derivative of both sides. And so when I take the derivative of both sides, I'm going to get a ds dt. So I'm going to go ahead and take the derivative of my position function here. So s prime of t is going to equal 50 times 2t, and this is ds over dt. And I'm going to write this as 100t and then ds dt. Okay? All right. And then we're talking about evaluating at time is equal to 10. So s prime of 10 is going to equal 100 times 10, and then I'm going to get ds dt. So this is 1,000 ds dt. All right, and that just makes this process a little bit easier. Okay, so when I take the derivative of tangent is secant squared theta, d theta dt is equal to, I'm going to write the 1 over 2,000 because it's a constant, s prime of t ds dt, which is kind of why I did this first, because then I can substitute in values. So we evaluated the derivative at 10 seconds to get here, because then I can substitute my values in. Okay, alrighty, so then I'm solving for d theta dt. S prime of t evaluated at 1,000 ds dt. Sorry, my ds dt goes away. So my secant squared theta, d theta dt is going to equal, there's the 1,000 from s prime of t evaluated when t is equal to 10. Let me scoot my paper up, I'm sorry. Divided by the 2,000. Now I need to solve for d theta over dt. So this is going to equal 1/2 and then 1 over secant squared theta, which is 1 over 2, and this is cosine squared theta, because that's easier. But I need theta, right? So if I say the tangent of theta is 5,000 over 2,000, all the zeros cancel. Theta is going to be the inverse tangent of 5 over 2, right? Okay. And then if I do that, I get 1.190 radians. And then if I substitute in to get here, I get that d theta over dt is going to equal 1/2. You can still see it. And then the cosine squared of my angle, 1.190. You would want to make sure that your calculator's in radians. So sometimes we have those brain farts. And when you do that math, and if you left, you can either do it in decimal form or fraction form. You're going to get 2 over 29. Now let's talk about our units. Change in theta. I did my theta in radians, and the unit of time is seconds. So my d theta over dt is going to equal 2 over 29 radians per second evaluated at time is equal to 10 seconds. Okay? So that one was a little bit more involved and actually had several different pieces. So sometimes you just have to be careful, really careful, and try to see how you can work through what you need and what you don't have. All right, that is it for today. Thanks for being patient. I will see you soon.